Hello, my name is Ohad, and I will present the paper Coupled Training for Multi-Source Domain Adaptation. This work was done under the supervision of Professor Chechik from Ilan University and NVIDIA Research. Unsupervised domain adaptation is a learning setup where we train a model on source domain but evaluate it on a different but related target domain. Unlabeled target samples are available during training, and we wish to use them in order to adapt the model from the labeled source domain to the unlabeled target domain. For example, train a model using data from simulation and use the model on real-world data. In practice, we usually have multiple source domains. For example, images may be taken under several lighting conditions. Medical data may be collected using different versions of a sensor. In all these cases, we wish to leverage the labeled data from all source domains. This domain adaptation challenge is often addressed by learning a joint representation of source and target domains. At the first step, we train a feature extractor using a discrepancy loss. The loss aims to erase information about the domain each sample came from. Then, we train a classifier on the source domains. At inference, we use the classifier on the target domain. This hard sharing of representation often suffers from negative transfer, where features that are useful for the source domains are learned even if they hurt inference on target domain. In our approach, we avoid hard sharing of representations and describe a soft sharing scheme. Instead of constraining source and target models to use the same features, we encourage them to make similar predictions on the target domain. Let me describe the components of our approach. First, we have a teacher network. A teacher network is trained using labeled data from the source domains. Then, the teacher predicts the labels of the target domain samples. Then, the student is trained using the target domain samples and the labeled produced by the teacher network. Note that the student network is trained only on the target domain, so it has no direct access to the source features. This reduces negative transfer. In our paper, we showed the weak coupling exploits the distribution over unlabeled target data. Let me illustrate that. Let's say we want to train a classifier to classify the blue dots from the red dots. This will be the source domain. And assume there are also some unlabeled samples, gray X's, as a target domain. A model trained only on the labeled samples classifies perfectly the labeled source data, but ignores the target data. Here, using a simple dataset, we trained 20 models, each one with a different initialization. Each colored line corresponds to a decision boundary of these 20 models. The teacher learns to classify the source data and at the same time avoids dense areas of the target distribution. In the paper, we proved this effect analyzing the teacher gradients. We evaluate our approach on 4 multi-source domain adaptation benchmarks: Digits, Amazon Reviews, Office Caltech, and DomainNet. We find that our approach consistently outperforms current multi-source domain adaptation state-of-the-art, sometimes by a large margin. This paper describes a new multi-source domain adaptation method. Separate networks are trained while weakly coupling their predictions. We showed that this weak coupling moves the decision boundary to low-density regions in the target distribution. Evaluated on 4 multi-source domain adaptation benchmarks, we find that our approach achieves new state-of-the-art results.